the next thing we're going to discuss are recursive formulas. Now, recursion shows up frequently in math, and in general, what we mean by recursion is in order to move on to, say, a next step, we need to take what happened in a previous step into account and use that to figure out the next step. And we're going to look at three different interpretations using recursion. We're using recursive formulas in recursion. Now, the first one will look like this with general functions. Suppose f of 0 equals 3. This gives us a starting point. F of 0 equals 3. F of n equals 2 times f of n minus 1 plus 3. And we're going to find f of 3. So notice in this second one, notice this second equation exhibits recursion, because f of n is depending on f of n minus 1. So we need f of 3 here. Well, f of 0 is given to be 3. The next thing we can find is f of 1, because notice here, f of 1 depends on f of 0. So it's 2 times f of 0 plus 3. What's f of 0? Well, f of 0 is 3, so it equals 2 times 3 plus 3, which is 6 plus 3, which is 9. Well, there's f of 1. We need f of 3. The next thing we can figure out is f of 2. F of 2, still going back here, n equals 2. So we have 2 times f of 2 minus 1, so 2 times f of 1, plus 3. What's f of 1? Well, we found in the previous line that f of 1 was 9. So we have 2 times 9 plus 3. 18 plus 3, 21. Well, we didn't want f of 2. We wanted f of 3. So let's find f of 3. Let n equal 3 here. F of 3 is 2 times f of 3 minus 1, so 2 times f of 2. Still plus 3. That 3 doesn't change. What's f of 2? Well, in the previous line we found f of 2 is 21. So 2 times 21 plus 3, 2 times 21, 42, plus 3 is 45. So we can define functions using recursion. Now, a recursive setup could look different than that. So let's look at something else. I'm going to need 2 boards, I think, for this. So next we're going to consider an array of numbers which is defined recursively. And we're going to call it Pascal's triangle. Pascal was a mathematician. He also did physics. I think he also did philosophy back in like the 1600s, 1700s maybe. And he was not the first who was known to use this triangular array of numbers, but it is named after him. He had results using it, and well, it's named after him. Now, how is it formed? Well, it's going to be a triangular array of numbers. I'm going to form it like this. I might skew it a little toward that way, meaning I'll probably put the point on this side of the break in the boards. But how are we going to form it? Well, we're going to start with 3 ones in a triangular form, like this. And we're going to mark off the rows. The first row, just the 1, we're going to call the 0th row. So here we're going to start our counting at 0. And I'll explain a little on that in a moment. this row with 1, 1 is going to be first row. The row underneath it, which is not written, will be the second row, even though it looks like it'll be the third row. But we're starting counting here. Now, how are we going to form the next row? Well, we're going to use the previous row to figure it out. But first, we're going to start by continuing our triangular ones, meaning we're going to form the outside of our triangle using ones like that. But in between them, we're going to add the two numbers immediately above it. So notice in the first one we have 1 entry, here we have 2 entries. This next one we're going to have 3 entries, start with a 1, end with a 1, and in the middle is going to be the sum of that number and that number. The 2 immediately above it, that sum is 2. And there's the second row. Now what's the third row? Again, our counting starts at 0 for this. What's our third row? Well, again, we're going to start and end with 1s. I think the third row is where it starts. I don't think the second row is all that. I like the third row and beyond much more than the second row, because it really, in the third row, you start to see the pattern forming more than in the second row. But between these ones, well, first we're going to have 4 entries here. It's going to be 1 more than the previous row. But in each entry, we're going to look at the 2 numbers immediately above it and to the diagonal. So here we have a 1, we have a 2, those add to 3. Here we have a 2, we have a 1, those add to 3. And we're going to keep forming rows like that. 1 at the beginning, 1 at the end, and then we look at the 2 numbers above it to form, or to find our middle entries. So what would the fourth row be? Well, start with a 1, end with a 1, entry, entry in the middle, entry over here. 2 immediately above it, 1 plus 3 makes 4. 2 immediately above this, 3 plus 3 makes 6. 2 immediately above this. Now, immediately above is going to always make a formation like that. It's going to be, above and to the right, above and to the left. 3 and 1 make 4. Let's keep going until I can't keep going unless I write on the wall. How about the fifth row? Looks like I'll be able to get 7 rows. Fifth row. Well, 8 rows, including the 0th. Well, again, start with a 1, end with a 1. Next entry, 4 plus 1, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. And even the last rows you could think of as the 2 immediately above it, because in this direction it's a 1, in that direction is a 0. You could think of that like that if you want, as long as you start up here with a 1. Let's do the 6th row. Start with a 1. Next one is 5 plus 1, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. 1 plus 0, 1. And let's make the 7th row. Start with a 1. 1 plus 6, 7. 6 plus 15, 21. 15 plus 20, 35. 20 plus 15, 35. 15 plus 6, 21. 6 plus 1, 7. And we'll end with a 1. And this keeps going. You can keep going for any number. Well, positive whole number. Now, this array of numbers, triangular array of numbers, has many, many properties. It shows up all over the place in math, especially in a field called combinatorics, which is a large, fancy word for counting. But this shows up in algebra, shows up on combinatorics, shows up in number theory all over the place. It shows up really everywhere it could show up in some context. We're going to look at one way we can use it, but there are many things you may observe about it. First, each row is palindromic. That's true because it starts off palindromic and it forms in a palindromic way. Like 1, 3, 3, 1. 3 is 2 plus 1, but it's also, it's 2 plus 1. It's also 1 plus 2, and so on. Many properties this shares. The sum of each row, just look at the sum of each row. 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. But we're going to use this to expand binomials. So let's look at, 2 examples maybe? Yeah, let's do 2 examples. Expand each binomial using Pascal's triangle. What's a binomial? Well, it's 2 things added together, 2 variables, let's say. So first we'll do x plus, let's actually do 3 examples. Let's do x plus y squared. Let's do x plus y cubed. And let's do one more after that. Now, how are we going to do this? Well, now first of all, expanding binomials, you could use your algebra to do this. You could actually write out x plus y times x plus y and multiply all that, add the things together that go together. But we're going to use this triangular array of numbers. Now, how are we going to use it? Well, first, I should have told you to write, leave a gap between these two, because I'm going to write something here and then something here. Actually, you may be able to fit it all on one line. The second one you may not be able to. Well, how are we going to do this? Well, first we're going to look at the exponent. The exponent here is 2. That's going to tell us which row to look at. We're going to look at the second row where the top is the 0th row. So for this first one, we're going to look there. That tells us some good information. What information does it tell us? It tells us coefficients. It tells us the first coefficient is going to be a 1. It tells us the second coefficient is going to be a 2. Tells us the second coefficient is going to be a 2. It tells us the third coefficient is going to be a 1. First coefficient is a 1. Second coefficient is a 2. Third coefficient is a 1. Coefficients of what? Well, we'll see. But we look at the exponent, and we go to the corresponding row. It gives us this information. Now, these are coefficients of certain quantities. What quantities? Well, we look at our x and y in this case. Our first quantity is an x. Our second quantity is a y. And how are we going to use that? Well, right here is an application. It looks like an algebraic application, but we're going to treat it as a counting application, a combinatorial application. That word combinatoric, C-O-M-B-I-N-A-T-O-R-I. The noun combinatorics, the math of counting, the adjective combinatorial, the adjective form of the math of counting. And we're going to treat this combinatorially. Now, what do I mean by that? Well, we have an x and a y. The exponent tells us a little more information. It tells us each of these coefficients is going to have 2 letters attached to it. Which 2 letters? Well, we'll start with the x's, because they're first. X's are first. We're going to put 2 x's here. And then we're going to put 1 x here. And then we're going to put 0 x's there. 2 x's on the first, 1 x on the second, 0 x's on the third. Well, and then we're going to fill in the rest with y's. We need 2 total letters. We already have 2 letters here. How many y's do we need to make it 2? 0. 0 y's and 2 x's. Remember, exponents just count the number of things that are there with multiplication. 2 x's, 0 y's make 2 total letters. What do we need here? Well, we have 1 x. We need another y. What do we have here? We have 0 x's. We need 2 y's. So the way I just described it was get 2 total letters. There's another way you could get there. Now we went with the first thing 2, 1, 0. With the second thing 0, 1, 2. And this simplifies a little. You know, when there are 1's in math, you usually don't write 1's. Well, it's common to not write 1's in math. 1 times x squared y to the 0 is 1. Anything except 0 to the 0 is 1. So we have 1 times something times 1. So it's just that something. The next thing, x to the first, y to the first. You know, you don't write to the first. You just, you know, right here, there is 1 x, there is 1 y. So writing the extra 1 is redundant. And then the last thing is 1 times y squared. So we have x plus y all squared is, you know, the relation that in algebra class you were probably told many times to memorize it. And some of my calculus students didn't listen. But here we have another way we could get to that formula. The, what's it called? The square formula or something. Now let's do the same thing but with a cube. I'm going to have to write this one a little smaller. X plus y cubed. Well, again, we go to the exponent. The exponent is 3. That tells us we're going to look there. That gives us our coefficients. 1. 3, 3, 1. And then we look at our x's and y's. Here we're going to attach 3 x's to each thing, or 3 letters to each thing. Total x and y. First thing, we're going to put 3 x's. The next thing, we're going to put 2 x's. The next thing, we're going to put 1 x. The last thing, we're going to put 0 x's. And then we do the same thing with y's in reverse. 0 y's, 2 y's. 2 plus 2 is not 4. All right, wow. 2 plus 2 is 4. It's 2021, not 1984. 2 plus 2 is not 3. 2 plus 1 is 3. Or you could do 0, then 1. Here we need 2 y's. Here we need 3 y's. And then just not writing all the 1's. This first thing, 1 times x cubed times 1, gives us just x cubed. Next thing, plus 3, x squared y, plus 3, x y squared, plus y cubed. And that was probably a formula you were also told to memorize, but I never liked memorizing that. I think this one is way too much to memorize, plus it doesn't show up as much. But there's another way you could arrive at that. Let's do one more. Let's do a larger number. And we'll see that the pattern is the same. Yeah, let's do that. Next example, x plus y. Let's do, well, we have 7, so why not? Let's do 7. Now let's do 8th. Yeah, let's do 8th. I can fit in the 8th row down here. Let's get the 8th row. 1, 8. Well, here, I'll fill it in while covering it, and you can fill it in your notes. and compare it to what becomes uncovered. Oh god, I can't add numbers. What is this? I should have used 7, because then it would be prime like the other two. But I already wrote 8, so let's do 8. So the 8th row, we have 1, 8, 28, 56, 70, 56, 28, 8, 1. Before going on to that, I guess I'll just mention... Well, I'm going to... No, let's do this, then I'll mention what I was about to mention. Yeah, I'll mention what I... Yeah. We need the 8th row, so I'll just erase everything else. You know, everything we're doing here is just going to be x plus y, you know, for the lecture. For the worksheet, there will be a little more. But I'll make a remark on that in a moment. Equals what? Well, let's write these numbers. 1 plus 8 plus 28 plus 56 plus 70 plus 50... No, that's not going to fit. How many numbers? 9? 6 plus 28 plus 8 plus 1. I'll do it like that. 1, 8, 28, 56, 70, and so on. Well, the exponent 8 tells us how many letters we need on each thing. So we're going to need 8 x's, 7 x's, 6 x's, 5 x's, 4 x's, 3 x's, 2 x's, 1 x, and 0 x's. And then the same thing with y's in that direction. 8 y's, 7 y's, 6 y's, 5 y's, 4 y's, 3 y's, 2 y's, 1 y, and 0 y's. And then we'll just simplify this so that the 1's aren't there. X to the 8 plus 8, x to the 7, y, plus 28, x to the 6, y squared, plus 56, x to the 5, y cubed, plus 70, x to the 4, y to the 4, plus 56, x to the 3, y to the 5, plus 28, x to the 2, y to the 6, plus 7, x, y to the 7th, that shouldn't be a 7, that should be an 8, plus 8, x, y to the 7th, plus y to the 8th. So all of our examples have had just x plus y. You know, if it were, you know, x plus 5y, well, every time you put a number of y's, you'd also have to put that number of 5's. So in this case, you'd have a 25y squared. In this case, you'd have a 5y. Here you'd have a 125y cubed. Over there, and so on. But with the counting argument, now that's kind of implicit in the counting argument, because all I said was you don't need, well, I guess I said you need 8 x's and so on, but what you really need are 8 of those things, 7 of those things, 6 of those things, and so on, and in the other direction you need 8 of these things, and so on. So it's always, you know, in these binomials, we're going to have something plus something else. We're going to have 2 separate things. And Pascal's triangle is used to get the coefficients, and then it's used to say how many of each of the 2 things show up. So, I could throw a 5 on it like that. I wouldn't throw a 5 to the 8th like that. I'd use a reasonable number. But you could also, if you had a negative y instead, how would that change? Maybe I'll use to the 3rd since you're taking notes. Well, since you might be taking notes. Now, if you're taking notes, I'm not going to make you rewrite that long equation. But let's do a 4th example, x minus y cubed. What would that be? Well, using the 3rd row, the coefficients are 1, 3, 3, and 1. And then what? First thing is an x. 3 x's, 2 x's, 1 x, 0 x. What's the other thing? Well, the other thing here is a negative y. 0 negative y's. 1 negative y. I'm going to write that. I don't want parentheses all over the place. 1 negative y. I'm going to put the y there and the negative there. 2 negative y's. Well, negative y times negative y, positive y. 3 negative y's. 3 negatives multiplied make a negative. And if you just simplify this, you get x cubed minus 3x squared y plus 3xy squared minus y cubed. But what I wanted you to notice, with a negative, the signs are going to go positive, negative, and so on. If it's positive, everything's positive. But if you throw a negative on the second term, it'll change positive, negative, because every time you throw an odd number of them on something, an odd number to or a negative to an odd number power is a negative. So that's a second kind of recursion that we could see. Let's look at one more example of something defined using recursion. It's also something you may have seen before. Fibonacci sequence. The Fibonacci sequence is a sequence of numbers. It's a pretty famous sequence of numbers. It's defined recursively. Now, Fibonacci was not the name of a mathematician. His name was something else. It was, I forget, it's something Italian. I think it's like Leonardo something. I forget his name. But through time, he became known as Fibonacci. I think he was related to someone from a place that sounded like Fibonacci or something. But he was, the mathematician currently known as Fibonacci was around in the 1100s or the 1200s, and he was probably the most famous, I would say the most consequential mathematician of his time. He was Italian, and he was one of the first who began using the Arabic numerals rather than the Roman numerals. And then a couple hundred years later, math soared throughout all of Europe. But one of the things he studied was this sequence. Well, one of the things he used was this sequence of numbers. It showed up when he was looking at rabbits, I believe it was. He was looking at, he was counting numbers of rabbits, and he noticed these numbers showed up somehow. But how are they defined? Definition. The Fibonacci numbers are defined. How are they defined recursively? F sub, we'll use capital F, 1 equals 1. F sub 2 equals 1. And F, this might be where well, I'll stand in front of it. I have lamps in here lighting up my boards. The overhead lights create glare. The Fibonacci numbers are defined by this recursive relationship. F sub 1 equals 1, the first Fibonacci number is 1. F sub 2, the second Fibonacci number, is 1. F sub n plus 1 is F sub n plus F sub n minus 1 for n greater than or equal to 2. If n equals to... yeah, okay, for n, I was just making sure the indices matched up. For n equals 2, notice it gives you F sub 3 relating F sub 2 and F sub 1. So example, find some of them. Find some, well, I'll just, let's just say like find F sub 18 or something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's find F sub 15. No, F sub 16. No, F 17. Let's use a prime number. I have 15 of them written out here, so let's find the 17th number. And I'm going to do it, I'm going to write them like this. 1, 2, there's F sub 2. What's F sub 3? Well, let's show the computation for F sub 3. Let n equal 3, or let n equal 2. It gives you F sub 3. It equals F sub 2 plus F sub 1. F sub 2 is 1. F sub 1 is 1. F sub 3 equals 1 plus 1, which is 2. Okay, great. There's 3. What's the fourth one? We need the 17th. F sub 4. Let n equal 3 here. It gives you F sub 4 equals F sub 3 plus F sub 2. What's F sub 3? F sub 3 is 2. F sub 2 is 1. F sub 4 equals 3. So notice here, to find F sub 3, we looked at the previous two numbers and added them. To find F sub 4, we looked at the previous two numbers and added them. And that's how this sequence is defined. The next number is the sum of the two before it. So in particular, F sub 5 is F sub 4 plus F sub 3. F sub 4 is 3, F sub 3 is 2. So it's 3 plus 2, which is 5. And so on. So for the rest of them, I'm not going to write them all out like this. I'm just going to fill out the sequence. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3, 5. 5 plus 3, 8. 8 plus 5, 13. 8 plus 13, 21. 13 plus 21, 34. 21 plus 34, 55. 55 plus 34, 89. 89 and 55 is 144, which is 144. 144 and 89 is 233, because, what, you take 11 from that? That's how I would add them. And add 100. This plus that is 300 plus 77. 377. How many have we written? 1, 2, 6, 8, 9. Not enough. 233 and 377 is 600 plus 100, 500 plus 110. So 610. 610 plus 377 is what? 987. Is that enough? How many? We need F17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the next one is 17. The next Fibonacci number is 1597. So this sequence of numbers, very important, shows up not just in math a lot, shows up in nature a lot. I took this example from online. These numbers show up as the number of petals on a flower very frequently. And online it said there's a flower with one petal called a white calla lily. Never heard of it. There are flowers with 3 petals, including irises and lilies. There are flowers with 5 petals, buttercups and wild roses. There are flowers with 8 petals, delphiniums. There are flowers with 13 petals, ragwort and, I can't read my number, corn marigold? I said number, I can't read my letters. I think that says corn marigold, I don't know what that is. But it said it has 13 petals. There are flowers with 21 petals. Asters and black-eyed Susans have 21 petals, apparently. There are daisies with 34 petals. There are daisies with 55 petals. There are daisies with 89 petals. Now, not all flowers have this number, but have one of these numbers of petals, but it shows up amazingly frequently. There are some flowers with 4 petals, and 4 is not a Fibonacci number. But you know, the number of petals on flowers is one area where these numbers show up in a seemingly strangely large, well, with a seemingly strangely large frequency. I think that was said properly. That's one area that they show up. Other places where Fibonacci numbers show up. Leaf arrangements. So when a stem is, growing and leaves are sprouting out of the stems, the way they become arranged, the way the leaves are arranged going around it, follow a pattern relating to the Fibonacci sequence. Snails, in their shells, have a pattern related to the Fibonacci sequence. We'll talk a little about that in a moment. Seashells as well. DNA, the double helix, forms in a way related to one of these, a drawing I'm going to do. Also, many fruits and vegetables exhibit Fibonacci numbers in certain ways. Bananas. Most bananas, every banana I've seen is divided into those 3 segments. Online it said there are bananas with 5 segments. I've never seen one. But 3 and 5, both Fibonacci numbers. Cauliflower and broccoli. I'll describe something else first, and then I'll talk about that. On Canvas, I posted 2 pictures, and I have them on my computer over here. I posted a picture called peacock, a picture called pine cone. And on both of those pictures, the Fibonacci numbers show up. So I'd like you to go to, right now, pine cone. So take a moment to open that. You might have to pause this. On the pine cone picture, there are 2 pictures of the same, these are not my pictures, 2 pictures of the same pine cone. You'll notice at the top, one of them says 13 and the other says 8, both Fibonacci numbers. Now, what are those 13 and 8? Well, the 13 counts a spiraling pattern on the pine cone going in the counterclockwise direction. Now, this sequence of, what are those, pine cone leaves, whatever those things are called whorls. So this spiral pattern around, starting somewhere and going to the next one in a counterclockwise way or a clockwise way, these are called whorls. So in the first case, going counterclockwise, there are 13 whorls. A set of those is a whorl, W-H-O-R-L. Going in the counterclockwise way, there are 13 whorls. Going in a clockwise way, there are 8 whorls on that particular pine cone, and in general, pine cones will have a Fibonacci number of whorls. I believe it's always 13 and 8. And 21 may show up. I doubt 5 would show up. That might be too small. But pine cones exhibit property. The Fibonacci numbers show up in pine cones. And also, if you go over to the picture called peacock, and you open that up, again, not my picture, the circles on the tail, there's probably a technical name for the circles on the tail of a peacock. I don't know it. I'm not a biology person. But the whorls that you get by going from one circle to the other in a clockwise fashion. So the person who made this just took a line and connected them circle to circle in a clockwise and a counterclockwise way. You can see that in the second picture. But then in the third picture, they got rid of the peacock altogether. And in that, you notice the pattern, but you also, if you count the number of, I'm colorblind, I don't know what color they are, blue and pink. That could be anything from purple to green to blue to pink, maybe brown, or a color I didn't mention. But in both directions, if you count the clockwise or the counterclockwise peacock whorls, there are, I believe it's 13 in each case. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 going clockwise, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13 going counterclockwise. Both, well, 13 is a Fibonacci number. Now, that same type of behavior is exhibited in pineapples. The pine cone behavior shows up in pineapples. So if you, I don't have a pineapple. I almost bought a pineapple earlier today. I should have thought of using that for this talk. But if you take a pineapple, you look at the bottom and count the whorls, that'll be a Fibonacci number in each case, the clockwise whorls and the counterclockwise whorls. Cauliflower. The cauliflower and broccoli both exhibit a similar whorl pattern. It's harder to see with them because, you'd have to dig into the broccoli and the cauliflower. But a Fibonacci number shows up in each of them. Also, according to the internet, Claude Debussy, a musician, a French musician from the late 1800s, early 1900s, apparently he somehow used, maybe not used, but these numbers somehow show up in some of his music. Maybe some of you could figure more of that out than I can. I do not like Debussy's music. I find it awful, even what's considered his best. So I'm not going to look for it. But his music apparently exhibits it. Also, it's said some of Mozart's sonatas exhibit the behavior relating to these numbers. I haven't been able to figure that one out. I've listened to Mozart sonatas many times. I don't know what they're talking about, but they did say that he was aware of these numbers, and in his composing, he used them somehow. Maybe he, used patterns relating to 21 or something. Also, the Stradivarius violin, in its construction, some of its ratios are related to these Fibonacci numbers. So these numbers show up really a lot more frequently than you may expect that they would. And it's not completely known, for example, why they do. There are some theories that, like when a plant is, spreading its leaves out, if it does so in a way where there are like 3 in this direction and 5 in another direction, that it may get optimal sunlight. But they're not, it hasn't been shown conclusively that that's guaranteed. But let's use these numbers to construct what's known as the Fibonacci spiral. And this spiral shows up on a snail. It shows up in ears. It shows up in seashells. It shows up in hurricanes. And you'll see why in a moment. So let's construct the Fibonacci spiral. Let's do it on where? Let's do it on this board. How are we going to start it? Fibonacci spiral. Let's start with two 1x1s. I'm debating which way I want it to look so that it'll look the best. Okay, let's start with two. Oh, I shouldn't have erased those numbers. Let's start with two 1x1s like this. They're two 1x1 squares, representing the first two Fibonacci numbers. Well, next we're going to put a 2x2 square. This 1x1 and this 1x1 make 2 inches. So we can put a 2x2 square. I'm going to put it up here on top. So I'm not going to write inside these squares because I'm going to write something else in a moment inside them. But I'm going to keep track. This one right here, I'm considering as my first square. This one I'm considering as the second square, meaning the one going with the first number, the one going with the second number. This 2x2 will be the third square. Well, the next square, 3x3, here's a side with length 3. We're going to keep going in a clockwise way, adding squares on. So you could technically add a square over here because that's a 3-inch thing, or well, a 3. But I'm going to start here, go here, go here. Next one will be over here. This one will be a 3x3. And we're going to keep doing that in a clockwise way. 3x3, the next one is down here. What's that? That would be 5x5. Let's make it look more squarish. That doesn't look much more squarish. The next is an 8x8. Notice here is a 5x1x2. So that will be an 8. And on top, the next one, we're going to put a 13. Like that. Maybe I should make these. I guess I'm going to have to erase that. I'm also going to erase that to make that side look a little square. And up here, a 13x13. And you can keep going. 21x21, 34x34, and so on. But what are we going to do with this? Well, we're going to form a spiral. How are we going to form a spiral? Start up here. And we're going to go diagonally, but we're going to make an arc. And we're going to start at the largest square we drew. We're going to make an arc like that. We're going to keep going diagonally across the next square. Make an arc like that. Diagonally across the next square. An arc like that. And we're going to keep going diagonally across the next square. Make an arc like that. Diagonally across the next square. An arc like that. Diagonally there. And diagonally up to the last one. And right here, you could see what would happen if you keep going. It would make, keep making a spiral like that. And this is called the Fibonacci spiral. And maybe I should have drawn a little differently so that you could see how it's an ear. If you're writing this on paper, take it and rotate it 180. How many degrees? Rotate it clockwise. 180 degrees. You can see how it looks kind of like the inside of an ear. Or it looks like a seashell, some seashells. Or it looks like a hurricane. When you see the, from the satellite view of a hurricane, or not the satellite, when you see, like on the Weather Channel when they have a hurricane. The rain pattern for a hurricane kind of looks like that, related to Fibonacci spiral. That's a large hurricane given the East Coast. So that's another. I think that's a cool thing with the Fibonacci sequence. I like the Fibonacci spiral. We're going to do one more thing. We're going to consider one more thing with this Fibonacci sequence. Example: consider ratios of consecutive Fibonacci numbers. Consider ratios. Well, what do we mean by this? Well, I have them written out here, so I'll use these. Second one to the first one, 1 over 1. I'm going to write something underneath this also. Third to second, 2 to 1. Fourth to third, 3 to 2. 1 to fifth to fourth, 5 to 3. Sixth to fifth, 8 to 5. Seventh to sixth, 13 to 8. The next one, 21 to 13. How many did I write out here? That's the last one I wrote out. You can keep going, 34 to 21, 55 to 34, 89 to 55, and so on. But these numbers, now I like fractions much more than decimals because they're much more useful in all contexts but comparing. They're much harder to compare immediately. But let's look at the decimal for each of these numbers. Well, I can do the first 4, 5. First one is 1, second one is 2. This is 1.5. This is 1 and 6, whatever, repeating. This is 1 and 6. This is, I guess I can't do that, 1, 6, 2, 5, yeah. 1 and 6, 2, 5. This next one I can't do is 1 and 6, 1, 5. The reason I can do this is actually because of baseball. If someone goes 5 for 8, they're hitting 625. And so on. These numbers approach a number. So you can see that 1 to 2, these will keep, they kind of oscillate around something. These numbers approach a number. So, a sequence approaching a number is technically an end of Calc 2 topic. But you can imagine this continues. This approaches a number. What does it approach? I will tell you what it approaches. This sequence approaches what is known as the golden ratio. The golden ratio. And what is this golden ratio? 1 plus root 5 over 2, which is approximately equal to 1.618. I'll just say it just keeps going. So it's an irrational number. It doesn't have a finite decimal expansion. Approximately 1.7. Golden ratio, 1 plus root 5 over 2. Maybe I'll write that. I'll write a couple more. Why not? Because this one has 3 decimals, so I should put a little more in this one. 0.033, and so on. Now, why is it called the golden ratio? Well, they call it the golden ratio because apparently a rectangle with sides in proportion 1 to the golden ratio is the most aesthetically pleasing rectangle. It looks, something like that. Although not exactly like that. So it's said that it's the most aesthetically pleasing rectangle. That's one reason that's important. The golden ratio also shows up in math a good amount, a lot in math. One area that it shows up in math I'll just say remark. The golden ratio, not ration, ratio, is the ratio, not ration, is the ratio of what to what, I'm going to call it A to B in this diagram. So it shows up a lot in math. This is just one area. Take a regular pentagon. We've actually seen this diagram. Take a regular pentagon. Well, take a complete graph on 5 vertices where they're arranged in the form of a regular pentagon. The golden ratio with a regular pentagon is the ratio of one of these diagonals. They're all the same because it's a regular pentagon. One of these diagonals to one of those sides in a regular pentagon is the golden ratio. And that's just one area that it shows up. Why does the sequence of ratios converge to 1 plus root 5 over 2? So I just told you it converges to that. Why does it converge to that? Well, I'll provide a proof. It does require some algebra, quadratic formula. But that's okay. Well, what did we take? We took ratio of one Fibonacci number to the one before it. What does this equal? Well, denominator is still fn minus 1. Let's leave that alone. What does the top equal? I should have written smaller. Yeah, okay. Fn to fn minus 1 equals what? Bottom is fn minus 1. What's the top? Well, fn is defined as the sum of the previous two. So fn minus 1 plus fn minus 2. So all we did, the top is the sum of the previous two. This fraction splits. How does it split? fn minus 1 over fn minus 1 plus fn minus 2 over fn minus 1. So it splits, this piece plus that piece. Well, what can we do with this? Well, I should have written slightly smaller. You may want to write in your notes equals what I'm about to write, but I don't have room for it. So I'm just going to erase. This first thing over here, fn minus 1 over itself, is just 1. That is 1. So what we have here is an equation. We're going to look at that piece and this piece. Fn over Fn minus 1. Large arrow means little calculus. Not important calculus as far as we're concerned. We're looking at what this sequence of ratios converges to. We're looking at what it approaches as it keeps going out. We're going to call that x. So this is going to go to x. It's the ratio of a number to the previous number goes to x. The Fibonacci, or the golden ratio approaches, we're going to say x. Using this equation, well, 1 is 1. What is this? Fn minus 2 over Fn minus 1. Well, this is a number divided by the one before it. This is that same thing flipped upside down. It's a number divided by the one after it. So in the end of the sequence, this piece would go to x flipped around, which is 1 over x. This goes to x late in the sequence. This is the same thing flipped around, because this first one is ratio of number to the one before it. This one is ratio of number to the one after it. So that's flipped around, causing us to flip the x around. And right here, x is our golden ratio. We need to solve this for x. Well, we can do that by making this a quadratic equation. Multiply everything by x, get rid of the fraction. Makes x squared equals x plus 1. So multiply this by x, x squared. X times 1 is x. 1 over x times x is 1. Put everything on one side. We're looking to solve this equation now. How would we solve that equation? Well, we can use the quadratic formula. It gives us x equals what? Negative of negative 1, which is 1, plus or minus the square root of negative 1 squared, which is 1, minus 4 times a times c, which makes positive 4, all over 2. So we get 1 plus or minus square root of 5 over 2. That's technically two numbers. The Fibonacci numbers are going to approach the positive of those because they're all positive ratios. 1 minus root 5 is negative. So the ratio will approach the positive of those, which is our golden ratio. So there was a little algebra. I'm not going to ask you to prove the golden ratio, but I think it's pretty cool how we have just these relations and we were able to turn them into an algebraic equation.